Okay, good. So let's start. So last time we've seen some classical parameter estimation. I'll just recall you quickly what we did. So the setting was that basically we had some experiment going on. So some probe is sensing some unknown parameter b, yes, and then we do some measurement on the probe, and this gives an outcome x. All right. Wait, I close the door. The window. Yes. Now the idea is that we know exactly what the physics of the system, so we know we have a model, so we know how the probability to get an outcome x is related to the parameter b. Yes. So this thing is just a probability distribution, so it lives kind of in the space of probability distributions on the simplex like this. It's a curve on the simplex, and basically then the idea is that we want to estimate the parameter from the observation of x. Yeah? So we get x, or maybe we get many copies of x in a many repetition scenario, and we want to track back to b. Yes, and we've seen that the very relevant quantity there is the Fisher information. The Fisher information for this distribution p x at b, which is defined as my girls are crying. Sum of k, so the derivative of this one squared divided by p. Right? So the classical scenario was quite clear. Now today we want to see how this works in a quantum scenario. In quantum scenario, basically things are quite similar. So the difference is that this step is not trivial, right? So the measurement step is not trivial. So precisely what happens is that we also have some probe, which is modeled by some quantum state, for example, and then it interacts with the environment, which contains the parameter information, and at the end we get some state which depends on the parameter, yes? Now for this state, again, classically a state, you can just read it out completely. So there is a trivial state between kind of what is encoded here and what you can read out. Now in quantum mechanics, of course, you know that it's really non-trivial because there are quantities which are not measurable simultaneously. So the thing is that we have to kind of choose a good measurement then and get an outcome x as well. Yes, which allows us to estimate the parameter b. This is what we're going to see now. Yes? Good. So let me erase this. Or maybe let me not yet erase this. Well, there's the difference that if here probabilities, they live on the simplex of probabilities. Now we have actually on this level here, we have a curve kind of on in a state space. Yes, so it's some convex set, and there is like a curve in the set of density matrices. Right, this is kind of where the parameter gets coded. Right. So all this physical model we have here is that we know precisely how the parameter for the input we select. We know precisely which state we're going to have here at the output. Now we have to select the measurement. And so the idea is that we just replace the curve in probabilities like this, which is given by our classical model, by a curve of density matrices, which is given by our quantum model, like the master equation solution, for example, as you did many times in the exercise now. All right, but well, so with keeping this in mind, one thing we can, since we're interested really about how optimal way to measure this, well, one thing we can do is just basically, and this is precisely what you do, is that we take, maybe I take black, it's the best one. Yeah, so I can just take a look for what we get. So there was this classical Fisher information, right? F of f like this, of p of x knowing b at b. And I can just fix the measurement. So I can just define, for example, something as like given this curve rho of b. Let me just I choose a PUM. I choose some PUM. I choose a POVM, right? So some measurement here at this point. This is PUM given by the operators ek, right? Okay, for example, equal to 0 to n with n outcomes. And I just now look, define it. So now with the choice of PUM, of course, my curve in the state of space, this just transforms by the choice of PUM to the curve on state of probabilities. Sorry, to the curve of probabilities, right? Okay. We cancel.
Yeah.
My daughter, sometimes they cannot play nicely. Yes. Okay. So whenever we fix a PVM, kind of we reduce the problem to what we've seen last week, right? Of course, the question now is what is the best PVM, but we can just again define it by optimizing the PVM, right? So let's just define the quantum fish information now like this. So I erase it and let's say that we just define it like this. So we have the quantum fish information, quantum Fisher information. We'll just define it as the best, as kind of definition, right? We'll say that this is the best, the maximal Fisher information. Fisher information for all POVMs, right? So in other words, we'll just write that now Fisher information for curve of states rho of B, right? This will just be the max over all possible POMs dk of yes, of the classical Fisher information, which was f of this probability distribution. All right. Sorry, again, choose letters. Where now precisely this p of kb is given by the Born rule. It's just trace of rho of b times dk. Right? That's very useful. Okay, we can do something directly with the definition because remember this classical Fisher information, we defined it as the substitutability of the fidelity. So right, this actually tells us, if you recall what we had last week. So this now is max of ek. So this was defined by the limit when the parameter is small. So dB goes to 0 of an expression like this: 1 minus f of p kind of b, drop the k. It's clear, right? And b times divided by b squared. There was probably a factor of 8 or something like this, huh? Okay, there was some factor here. I don't remember. Let me check the notes. Yes, precisely. There's a factor of 8. But you see now what happens is that if I can compute the limits here, so it's a maximum maximization in the limit, and actually I kind of for finite Hilbert spaces, I think you can always do this because the optimal measurement, which minimizes fidelity in the neighborhood of rho b, it's well stayed, so it's always the same. So if I compute them, you see what I can do is we can just change the order. Then we will recover the kind of the Ullmann fidelity, so the fidelity in the states, right? So I will just compute the limits. Then it's the limit of dB goes to 0 of the max, the best POVM, all right? And now you see, recall that the fidelity between the probability distributions which we obtained by doing some measurements, right? This is the best, so the best possible fidelity, in other words, the lowest fidelity, right, when they're the furthest apart. This was precisely defined as the fidelity of the quantum states, right? So now this expression, I can just write it as limit of dB goes to 0 of 1 minus the fidelity now between states, rho of b, and rho of b plus dB, right, divided by, right? So this is the substitutability of the quantum fidelity now between states, right? So now already we can rewrite it nicely, because this object we are used to it already, right? This is just how basically this is distance kind of. It relates to some distance on the space of quantum states, and then this quantum Fisher information just tells us how far this drops. Of course, again, now you have to be careful because now what happens here actually is that you see we have this curve now, rho b, and we say basically it's here to detect. So basically to see if changes of the parameters here, right, in this thing here in the tangent to the point B, there is some optimal POVM. Now you have to keep in mind that of course the POVM which will be optimal here at another B might be different. So already we see that there is some, especially if you're going to a Bayesian setting where you're just allowed to do like one measurement, and you don't know where the parameter is, this will be a bit tricky to, so not tricky, but we'll pay attention to this, and the POM has to be kept the same, because if you just maximize the POM for each point, of course, globally you cannot reach this. But we'll see it later in the basic case. Now, but around this point, everything works well. We can just define this quantum fish information is the best among classical fish information for all measurements, and then it just boils down to give the fidelity susceptibility. Yes? So this will be our definition, right? Of the fish information. And again, of course, now since this is the case, you can kind of use the Kramer bound, and you know that, and then we know that the mean squared error of the estimation is bounded by 1 over this fish information. Yes? So we'll give the definition. This will be again just the limit of dB goes to 0 of 8 times the how the fidelity decays. Right? Yes. Again, and this has all the nice properties of the classical fish information, because basically it's defined by the classical fish information. So the Kramer bound, and I don't know what you see except this. Well, at least the Kramer, but we'll see more in the future. Right. Well, first thing is just already we can try to compute it maybe for some example, just to see what this thing means. And okay, definition. Now, one thing we can do is already to do it for pure states. For pure states and unitary encoding. Yes, so let's do this for pure states. So example. And the example will be pure states. Pure states. And unitary encoding. In other words, now rho B, this curve is given by some unitary B times some Hamiltonian times the state. Yes. Actually, kind of this unitary encoding, where the parameter is encoded by Hamiltonian, this will be really mostly the object of our interest. You can, of course, define the fish information for any curve in space, but this is kind of what people usually treat in quantum metrology, or most often, because this is how kind of external fields enter, right? So, so if you have a field, really like a magnetic field, it will just couple with Hamiltonian. But so this is typical thing. However, of course, having this for pure state, this is really not really realistic, because in practice you will have some noise. So then, even so, the signal kind of the parameter of interest enters as a unitary, the states will not be pure. Okay, but this is it's a very nice example to see what the fish information is. All right, so let's just now write down the expression. So now we want to compute basically fidelity of rho of B and rho of B plus dB. Okay, well, first thing we can say is because fidelity is invariant under unit transformation on both things here, on both states. Yes, so this is equal to the fidelity of the states where we just, so the idea is just to cancel first this part, right? Rho of B. This will be rho of B plus dB. Yes, this comes from the fact that we are invariant under unit transformations. And of course, now if I plug in the definition, you see that what happens here is, well, this cancels things. So we have the fidelity between psi 0 state, yes, and a state, the rotated state. So the state which is E dB minus H psi 0 with plus. Yes. Now we've seen what is the fidelity between pure states, and the fidelity between pure states is just the absolute value of the overlap. So in other words, this thing is this guy here, dB H psi 0. Okay, so let's just compute this. No square, just absolute value. This we have seen as well. All right. So let's just compute this, and to do this, we just expand this unitary here in order of dB. Okay. So let me keep this here, and we will continue. Yes, so we get check psi 0 identity minus IDB H minus square root is so minus dB squared over 2h squared, right? So 0. Okay. Now this thing is what? This thing is we have a real part here, so we'll have the real part is size 0 because h is emission, right? It's an Hamiltonian. There is a real part, so we have 1 minus dB squared over 2h squared, size 0, right? Which is real plus I size 0 dB h, yes. So you rest on the absolute value of this. So this guy is real, this guy is imaginary, so we just sum the absolute square, absolute values of these guys, and then we get that this thing is 1 minus dB over 2, the expected value of h squared, right? So this is just h squared or psi 0 squared plus this guy, so plus dB h squared and the square root, right? On top of this, the square root. Well, and now I guess we get. So again, now we have to expand it in first order. So expand it in first order, we get a square root. So this thing is just okay. Let me just keep it first like this. There's 1 minus dB square here. H square, right? This is the leading order here. So we get the square, we get it 2 times. Plus dB squared, H squared, okay? Which is in the first order given by 1 plus 1/2 of dB squared H squared minus dB squared H squared. So this term, okay, you probably can't read it, but you get it, no? So we get just this, so we just get it twice, 1/2, because of the square root. Finally, it means that the fidelity between these two states. So for pure states like this in unitary encoding, we get that the fidelity between let's put it like this: fidelity between psi 0 and fidelity between E dBH psi 0, because basically this is what we boil it down to. This is just given by 1 minus 1/2 h squared minus h squared. So this is the variance of h, right, on the state psi 0. Okay? This is the variance of h on the state psi 0. Now, if you plug back in the definition of the Fisher information, then there was a factor of 8. Right, so I had that this is, what was it? 1 minus Fisher information of the state. Is 1 over 8, I guess. Yes, or is 8? This is not all. No, this is 8. Do you remember this is 1 over 8 or 8? Anyway, I know the answer. So the answer is that this is 4. So Fisher information of this guy now is 4 times the variance of the generator. Okay? Oops, sorry. So this already tells you good. So it's something very simple for a pure state, because for pure states you see that you can directly get the Fisher information with the variance with respect to, so if with respect to the Hamiltonian which generates the evolution. Okay. So let's just apply this now for qubits, for example, and see what it gives us, just to see if this makes sense. So let's just take this example now, and we take example 2. So we keep this pure states thing. So pure states, we get Fisher information of E, B, H psi. This is the curve of states, defined by this Hamiltonian. It's just given by 4 times the variance of H on psi. And we want to do it for qubits, just to see if this gives us what we kind of think, right? This corresponds to our intuition. So for qubits, we just take, well, so let's take our blocks here as usual. So we take some qubit state here, on the surface. So this state will be then psi, right? It's given by well, 1/2 sigma 0 plus this vector n times the power matrices. Okay. Well, let's compute the variance, and we say that now the Hamiltonian is actually, as we did in the example, we say that the evolution is rotating us around sigma z. Yes. So now we are sensing again a field which just rotates our qubit like this. And we want to see how well the qubit state here on the surface will be sensitive to this. What is its feature information? So let's just we just compute the variance again. So now, well, the variance of h by definition on the state psi. This is just given by h square psi minus psi h psi, right? Squared, okay, here. So this is given by trace of our Minsky matrix, 1/2 sigma 0 plus n sigma times sigma z, the Hamiltonian is sigma z, right? Squared minus, this is h squared here, right? This is this term, minus trace of state 1/2 sigma 0 plus n sigma or sigma z without the square. Right now you see that well, sigma z squared is just the identity matrix, so this trace is just 1 always, right? Because yes, because it's a normalized state, so this is 1. But this thing here is by using the orthogonality of the powers. You see that we have some overlap here from this thing from the power z. So this guy is equal to trace of 1/2 nz times sigma z, sigma z squared, right? So in other words, this is just nz, because the trace of sigma z 1/2 is, so this is equal to nz. So in other words, we find that for a qubit, the Fisher information, it's 1 minus nz. And wait a second, it should be, yes, this thing is squared, right? So it's nz squared. Of course, right? So let's see. Square. So for just the very simple example, the most simple example, we just get the Fisher information. So the Fisher information of the state here on the block sphere of the state, yes, so this state psi with an encoding this Hamiltonian. It's given by 4 times 1 minus nz square. So what does it tell us? Basically, what is the best state which maximizes the Fisher information? Can you see it? So we have to basically put, right, so it's maximal when nz is equal to 0, right? So if you plot, this is the nz here. So if you plot nz, right, we have 0 here. On the extremities, so this is our kind of block sphere, then the Fisher information is -1, 1. And the thing is, we'll get, here we get 4, right? So for the state here, we get QFI equal to 4, right? For the plus state, or any state on the equator, actually. Whereas on the extremities, we just get 0. So this state is, say, 0 QFI, this state is 0 QFI. All right, so which is actually very intuitive, right? So clearly this state has 0 QFI because this state is actually an eigenstate of the evolution. So they won't even move. They won't encode any information about the parameter B, right? Because the Hamiltonian doesn't act on them. They cannot turn around sigma z. Whereas this state is the optimal one. So the one on the equator, which has the kind of the smallest z component and which is furthest away from the axis, which has the maximum Fisher information. So this corresponds to, I guess, what in the examples you've seen in the exercises, it was always the case as well that the plus state was always optimal to distinguish the presence of magnetic field, right? In the hypothesis testing scenario. So very nice. So now we have some. So it corresponds to our intuition, yeah. And again, it's clear that now with this thing, you could just use a Kramer bound to see what is the limit on the estimation of this parameter B. So we'll do it in the exercises now this week. Okay, so far so good. Do you have some questions on this? Or is it going well at the moment?
Yeah, just a little question. For example, about this value 4. Is there anything special about this value 4 for the Fisher information, or is just what we get after calculating what we had for a pure state?
Well, there is not. No, there is nothing special. It's just, you know, these things are all defined up to a constant, right? I mean, we get, for example, when we see that the Fisher information is defined 8 times the substitutability of the fidelity. I mean, the state is just pure operator. You can also define it with something. It just, I guess, historically it was defined like this. Yes.
Yeah. Okay. Yeah, just checking to see if that's the
just
case.
how these quantities are related, yeah? But there is no like deep meaning about it.
No, of course.
So what is, I guess, the Fisher information is really defined as expected. Classically, it's defined as expected value of the score. All right, and then when you relate it to all these fidelities, you get these factors. Yeah. But I wouldn't attribute any meaning to them.
Okay. Thanks.
Good. So now the point is that so we have our example. So we have a definition of the Fisher information, right? So the quantum Fisher information of the state rho B. I'll just remind it. This is equal to basically yes, the stability of the fidelity. So 1 minus f of rho B plus dB over dB square, right? So in the limit. Very good. With a factor of 8, of course. But actually, for pure states, it's the only case where this thing here is nice to compute, because you can imagine that for mixed states, it's kind of horrible to make this limit. In general, the fidelity is really not an easy thing to compute. I don't know if you, I mean, you made some experiments with this exercise with qubits, where one state was pure, the other one was mixed. Actually, first we wanted to do it with 2 mixed states, but then just a nightmare to compute this thing. So replaced one by pure states. So this expression actually kind of conceptually is nice because it gives you this geometric interpretation of what the Fisher information is. It's really how this kind of overlap decreases when you change the parameter along the curve. But basically, to compute, there is a much simpler equivalent definition. This is what we are going to do now, right? So the next 15 minutes. So this will be like point 2. It's a definition from a symmetric logarithmic derivative, what's called. From the symmetric, let me just write it down first. Symmetric logarithmic derivative. And then you will see that this is really much better for when you have to compute something. Good. Yes. And to do this, let me just look at this expression and see what it means. So we just write the fidelity between these two states, rho of B and rho of B plus dB, right? This is given by square, so by the trace, sorry, by the trace of the square root of rho of B, and here the square root. Sorry, this is just a definition of the fidelity, right? So B plus dB square root rho of B, yes. Now, of course, let's just call rho of B, we'll call it rho simply, no? And this guy here will expand it in orders of dB, right? Because that's what we want. So we will get rho of B plus dB. Right, usual thing is rho plus rho dot dB. So the first order contribution plus 1/2 double dot dB square. Yes. And basically what we want to compute is this thing. Good. However, actually it's still not easy to compute, so we'll define something else now. Let's just define so let's just define this operator which is square. So this is the square of this, right? So this thing here, we'll define it by f. So this will be f of dB, so this big operator, if we just write it down. This is what we care about. We care about the trace of this operator, right? Rho of B, square root rho of, rho of B plus dB, rho of B, Yes, and actually what is nice, because this is really quite an horrible expression, in fact, because there are so many square roots. But what is nice is that we know that f db squared, the square is kind of nice, because the square just removes us the big square root, right? So if you square this thing, we just get the square root of rho b. This, we know it from, wait, let me just write it down. So what we know is that we get here rho 0, so rho of b plus db. Is it true? Also, if you square this thing, wait, I managed to confuse myself. Yes, no? Yeah, because this is just the definition of the square root, of course, right? Good. So, yes, and this expression is nice now, right? So you see, because here we can plug our expansion of rho, and there is no square roots anymore to play with. So basically what we have here is that this thing here is just equal to rho, and then we get our rho plus rho dot db plus rho double dot half db square times rho. Okay. This is one thing. The other thing is that we can also now take this f and also expand it in order to db. Yeah, just independently. I mean, this is some operator which depends on this db, but nevertheless we can just expand it. So we'll just take this equal to f0 plus f dot db, right, plus 1/2 f double dot db square. All right. And now the nice thing is that we can kind of take so this is to the leading orders, right? Now let's just take this thing. So let's look here on what this is. So they're equal here, right? These two expressions. We just plug in the expansion. Now let's look on the expansion of this thing. And this thing here, we just expand this, so we get, well, okay, let me just write it down. F0 plus f, well, maybe the 0, then we don't need it, so just f dot db plus f double dot db square over 2 square. Okay, so this thing is, first order we get f square, yes. In the next order we get f dot, this f dot f db, this is the first order. So you just pick up the product of this thing. Finally, for the second order we get, well, first there is this guys here, so 1/2 f double dot plus the other order, 1/2 f double dot f plus this term squared, f dot squared db squared. Okay, so it's it's not straightforward, but you see that now this operators, of course, should the expansion should correspond. Okay, so we cannot just say that this guy is equal to this guy because the square. So, and this gives us 3 equations for each order. In other words, from this equality here, right? So from the equality of this thing here, we can get 3 equations, and the equations, they will be the equations. They will be first that yeah, sorry, there is a square root here, right? Of course, this was the thing. So first f square is equal to rho square, and this actually imply, well, we knew already that f at 0, so f at 0 is equal to rho. So this just implies that f is equal to rho. First order. Now next order we get something like this: f dot plus f dot f is equal to square root of rho dot square root of rho. Okay. And the final one is, so let me just write it down. We have to space, so we just copy the other term, and we get something like this: f double dot f plus f f double dot plus twice f dot square is equal to well, the other one which was square root of rho double dot square root of rho. Okay. Yes. Now, what do we want to do with this? It's a bit technical, so I have to read my notes to you as well. Basically, from this we want to show to get a nice expression for the, so because you remember the fidelity is just given by the trace of f of dB extended, right? So if you now use expansion here, you see that this is basically given by trace of f plus f dot dB plus f double dot dB square over 2. So this will just solve this one, so it's 1 plus trace of f dot dB plus the trace of the other one. So dB square over 2 trace of f. So first we have to solve that this is 0, and this will actually get there now. Actually, one thing which is easier to, as we did for fidelity, we'll first assume that rho is invertible, right? Which we're allowed to do, and then we'll see how to do it with non-invertible. So if rho is invertible, then we can just play with the first. We can just play with the first thing, because here, remember, you just replace f is equal to rho, so we get here rho, and right here, this will be equation 1, this will be equation 2. Okay, so from I, we can just multiply by the inverse of rho on both sides, right? For example, on the left, and then what we get is that we get f dot plus rho minus 1 f dot rho is equal to, so just let me assume, so first we assume rho invertible. Okay, and this is equal to rho minus 1/2 or rho dot square root of rho, right? So I just multiplied by the inverse of rho here on the left. You see, you get nothing here. Now we get this thing. Now we get here. We get the minus 1/2 power. Okay. If you take the trace of this already, you see that. So let's take the trace of this expression. Here we get the trace of f dot plus trace of rho minus 1 f dot rho, which is equal actually to the trace of f dot, right? By cyclicity of trace. So this is equal to trace of this expression here, rho minus 1/2, rho dot, rho 1/2. Okay. Which is, well, here cyclicity is the trace, so this goes on the other side, basically meaning that this is equal to the trace of rho dot, right? Same here, we can get this times this, so on the other side, rho is invertible, so we get 2 trace of f dot is equal to trace of rho dot. But of course, rho, it's a density matrix, so if you move along the curve of density matrix, the state stays normalized, right? So the trace of rho dot is 0. Otherwise, it will change the trace of the state, so it will change the normalization. So in other words, from this, we can already conclude that trace of f dot is equal to 0. Yes, so which is nice, because here in the expression, it means that this term disappears, and we are left with the fidelity. Yes, this term disappears, and then we are left with the things that the fidelity is equal to 1 plus dB squared over 2 trace of f. So basically, what we care about now is just to compute this trace of f double dot. Okay. Tricky. But we're getting there. So what else? What else do we want to see now is that yes. So then we will look on this expression here, right? And we will do the same trick. So we multiply it by square root of, we multiply it by the inverse of rho on the left, right? And we take the trace, okay? So multiply by, so multiply by rho minus 1 and take the trace. And then we get from here, we get the trace of fw, right? So rho minus 1 rho plus trace of fw, the 2 dots, plus 2 rho minus 1 f dot square is equal to rho minus 1/2. This is a trace everywhere, right? Rho double dot, rho 1/2. Again, using the cyclicity, we just get the nice expression that we have now 2 times trace of 2 times trace of f double dot from here and from there, plus 2 times trace of rho minus 1 f dot square is equal to the trace of this thing, but this thing is just a trace of rho double dot. Again, for the same reason that the first order, the trace shouldn't change. The second order should also not change because the state remains normality. So this is 0. And now we are almost there, because now, since this is 0, the term we care about here, so in other words, the trace of, this implies that the trace of f 2 points is equal to minus the trace of this guy. Trace of rho minus 1 f dot square. Okay, so here in our expression, we'll just replace it. So we'll just use it and replace it. So in other words, this is the fidelity is equal to what we want, actually. So we'll just put it in the corner. So the fidelity is the thing we want, which is equal to 1 minus dB square over 2, and the trace of rho minus 1 f dot square. Okay? Right. Good. So now I think we don't need the second equation anymore. We just have to play a bit more with the first one, and then we'll get our nice SLD formula, which we'll use to compute things. Yes, and to do so, we will kind of rewrite this first step here in another way, and we'll just say that this thing here, right? So the trace of rho minus 1 f dot square, right? Using the cyclicity again. This is equal to 1/2. Well, first, yeah, okay, let me just. So this is, of course, just trace of rho minus 1 f dot f dot. This is also trace of 1/2 trace of rho minus 1 f dot plus f dot rho minus 1. Right? Well, I didn't do anything here, just go over this term twice, put 1/2 here. Right? Both of them are equal. All right, now, finally, this thing here, you see, actually we can make it appear from this expression. Because this guy here, if we multiply this equation, so we take equation I, and we multiply by rho minus 1 on both sides. And this will give us the following identity, that rho minus 1 f dot from here plus f dot rho minus 1. This is equal to rho minus 1/2 rho dot minus 1/2. Okay. Nice. Now what was the last step? Yeah, the last step was just plug this expression here. Yeah, so, I mean, this will be the next step. So, since this is equal, we'll just plug it in here. Okay, so we get that this thing here, which we care about, is equal to the 1/2 trace of rho minus 1/2 rho dot rho minus 1/2. All right. Now we, yeah, so this will make it good. Nice. And the next step is what? Next step is to look at our expression again, I guess. Which was, wait, let me just erase this. Unfortunately. Yeah, guys, I'm sorry, it's a bit technical, but fact is we're going to use it a lot, so we have to prove it, right? But it's not fun, I agree. So our expression was rho f dot, what was, why did you erase it? Come on. Sorry. So our first formula was this guy, plus okay, and fidelity is equal to 1 minus this thing. So this is what we get here. Right? So here, let me see what we do now for the last step. What we want to do for the last step is that we look at this expression here and we multiply it by the inverse of rho 1/2 on both sides. Okay. So if we do this, let me just write it down here. Rho minus 1 f dot square. If you do this on both sides, then we get that rho minus 1/2 f dot. So no, sorry, we get rho 1/2. I just multiply it by inverse of rho square root of rho on both sides, so we get f dot square root of rho minus 1/2 plus rho minus 1/2 f dot rho square is equal to rho dot. Okay. In other words, this expression I can write it the following way: is that rho dot is equal to, you see, so here we get to rho times rho minus 1/2 f dot rho minus 1/2 plus same thing, rho minus 1/2 f dot rho minus 1/2 rho here. Okay, and this is actually called the SLD. So in other words, you see that this guy we have here, this guy we have here. So okay, if you just pass the rho, so okay, let me just do it again. So we'll pass the rho on the other side again. All right, so this is check rho minus 1/2 here. So this guy we have in our fidelity expression here. Let's just call it S here. Okay, this operator S, and you see that S is actually it all works out if S is a solution of this equation. So by definition we'll call this operator. So by definition we'll call this operator S now a symmetric logarithmic. So S is a symmetric logarithmic derivative. Symmetric logarithmic derivative. And this means that rho dot is equal to S rho plus rho S. This expression we have here, and if we find such an operator which satisfies this equation, right? Again, it will be unique because it's invertible here. Then what we get is that, right? So then the QFI from this expression, it implies that trace of, so that the fidelity is equal to 1 minus dv square over 2 trace of rho minus 1 f dot square, which we just seen is equal to the thing, which is equal to 1/2. Sorry, here. So this thing is equal to this guy. So if we put everything, then we get 1 minus dv square over 4 trace of rho dot times S. Okay, and this is actually a nice way to compute the efficient information. Okay, so let me summarize now what we just had. So because now in addition, this fidelity is equal to what? In terms of the efficient information, of course, this fidelity is equal to 1 minus dv square over 8 efficient information, right? In other words, we get the solution that the Fisher information of the state is equal to of this row of B is equal to 2 times the trace of rho dot S, where S is the solution of this equation. Okay. So it was a bit lengthy. I'm sorry. It's like this. It also shows that it's not so obvious to play with operators always. All right. So let me just summarize it. Could you follow? Or mainly, just not to summarize, what we get is the following thing. We get that the QFI, so for a curve, for a state curve like this, we get that the QFI of rho B is equal to 2 times trace of rho dot times S. S is called the symmetric logarithmic derivative because basically it satisfies the following equation. What did you have 1/2 here? I'm writing things too fast. Sorry again. Yes, we didn't have 1/2. Rho S plus S rho. Okay. So this is the story here. Why is it nice? Because actually it's often, maybe always, it's much easier to solve this equation first. So you take the density matrix, right? You compute its derivative, then you solve for S. So it's much easier to solve this S and then compute the efficient version like this, than really compute the fidelity as a function of B and then take the limit. So computation, it will be much easier. In fact, just one last step is that because we get this thing here, you see that we can actually, since SLD satisfies this equation, we can plug it here. And then what we get is that, right, we just replace it here, we get 2 trace of rho S plus S rho times S. So this is also equal to 4 times trace of rho S squared. Okay? Sign. Okay? Do we want to prove this statement? Well, now we just take our definition of all possible verifications. Let's take this expression here. So the fidelity between these purifications, phi and psi, this is equal to, for any two purification, you can just write it as the fidelity between the state square root of n, square root of rho, and some unitary tensor identity, right, acting on this maximum tangle state, and square root of n, square root of sigma, some other unitary tensor identity acting on the maximum tangle state. Okay, and just this is pure state we have here because they're relative purification. This is just equal to phi plus 1 over so n, right? The n just a factor goes out. Psi plus, and here we get what? Here we get V transpose dagger. So V transpose dagger is just V conjugate. Never mind. So square root of rho, sigma square root of rho, U transpose. So yeah, and this is all acts on Alice side. Yes. It's all acts on Alice side. Psi plus. Now let me just plug in the expression of psi plus. Yes. Or phi plus, sorry. This is just n sum over k. Yes, and we will get k Alice on this big thing. V conjugate square root of rho U transpose times k Bob. Right, so I just put this thing here, and here we get well, J A JB sum of 1 over square root of n, and here as well 1 over square root of n. So first thing you see already that right, this is deciding phi plus, and this is also phi plus with this thing acting on Alice. Well, you see already that the square root of n is here. Check. Now on Bob there is nothing acting, so it just gives you a delta on kj. So finally, the only thing we get here is sum of k Alice of this thing V conjugate square root of rho, square root of rho, square root of sigma, U transpose Ka. Or in other words, this is just, so okay, are you fine with this? Just some, so this is just trace of this thing. It's a sum on the order basis, so this is just trace of V conjugate square root of sigma, square root of rho, U transpose, alright, and which is equal to the trace of square root of sigma, square root of rho, and here we get something which is ut V conjugate, which we'll just call, let's call just this thing which is called trace of square root of sigma, square root of rho some unitary W, alright? Alright? Now you remember that we also proved that this thing actually is smaller or equal the absolute, so the absolute value of this, we can have absolute value everywhere here. Because it's, right, this is a small equal to the trace of precisely sigma and rho, right? Where it only works of the absolute value. Because here we have the trace of the absolute value of an operator, and here we have the trace of operator times some unitary absolute value. All right, we've seen it, I think, in the second lecture or something like this. Why? Because if you use a polar decomposition, well, basically you see that this can only be, so it's smaller or equal. Okay, let me just show it quickly. So we don't have much time. It's really simple. Okay. You use the Ibrid-Schmidt product and the Cauchy-Schwarz. So trace of AW, right? This is equal to trace of A squared W. And oh, no, wait, no, that's wrong. So I use the polar decomposition. A is equal to A times U. Okay, so this is equal to trace of A U W. Okay. This is equal to trace of A squared U W. Okay, now by Cauchy-Schwarz, this is smaller or equal than the trace of this guy's square, right? The norm of this operator is here, which is just the square root of trace of A times trace of square root of A UW times the conjugate, which is W dagger U dagger. Okay, so this goes away, and this gets here we get trace of A. So this trace is always smaller or equal than this trace, and there's actually equality precisely when this guy is 1, right? Because we have equality here then. This is just basically what all this means here is that indeed we show that the fidelity between purifications is actually smaller or equal, is equal to this expression here, right? And it's smaller or equal than the fidelity between states, rho and sigma, which is here the definition. And actually it's attained if it's attained when this when the product of this unitary here, right, which appear in the purifications, precisely corresponds to the polar decomposition of the thing. Okay. So indeed it's equal. So in other words, the max of the thing. So it's always lower bounded by the thing, but on top of it, for the maximal thing, it's precisely attained when the unitaries correspond. So we prove the limit theorem. All right. Good. Moreover, you can see here that you see the only thing which matters is the product of the unitaries. So of course we can just keep one purification fixed. For example, for the state rho, we can keep a purification which has nothing, just U like this. Okay. And still we are able by choosing the purification of sigma, we can still make it equal to the polar decomposition unitary here, right? So you don't need the maximum or all purification. You can fix one and just maximize over one of them. This is the second, right? Yes, so, okay, we proved the Units theorem, but again, it was quite long, unfortunately. But okay, we have more lectures, so it doesn't really hurt us not to go slowly. Finally, good. So now let me introduce the angle. So we'll take the angle. So angle between quantum states. And this will just define the angle between two states, rho and sigma, as being the R cos. So maybe I'm not sure if we introduced it already, of the fidelity between rho and sigma. Okay. Good. So for pure state, it's really simple. You can at least on the if you plot it on the block sphere, it will really be just the angle between the vectors on the block sphere, I guess. Right? Now maybe it's a factor of 2. Yeah, well, let's make an exercise on this. But first thing we want to show is that this is the distance, right? So what do you need for a distance? Because for a distance, well, we need that it's positive, right? Which is the case because our cos is positive by definition. Yeah, it's symmetric because fidelity is symmetric. And if it's equal to 0, then fidelity is equal to 1. In other words, the state are the same states. So it's only equal to, the distance is only equal to 0 if we have the same object. If rho is equal to sigma. One other thing missing for the only thing missing for the distance is then the triangle inequality. Yeah? The triangle inequality, which means that if you have 3 states here, rho, sigma, and tau, yes, and what we want is that the angle between rho and tau is not bigger than the sum of angles between rho and sigma, right? Which is a very nice feature to have, and actually it's required for a distance. So so now the idea is that we use Unit theorem to show this, and then we will, if we have time, but probably we won't, we will see how now it relates to the Fisher information and how nicely it can give us some speed limits on quantum evolution. So let me just think about how to organize it. Do we maybe skip the proof and I give you the result, or do we give the proof and then we skip the result? What do you think?
The proof in the script.
The proof is in the script, yes. The proof. Okay, so I'll just give you the sketch of the proof then. Okay, then you can read it in the script, and it's more important to discuss the result. The sketch of the proof is simple. Basically, we just take. So we have rho, sigma, tau, right? We take these purifications for them. So we'll get psi, phi, and gamma. And we take a purification, so right, this is so the fidelity between these two guys is the minimum between the distance of these purifications. So we fix the purification of sigma to be phi, and we minimize these things, right? So these 3 states, 3 purifications are such that f of rho sigma is equal to psi phi, right? And f of sigma tau is equal to phi gamma, right? So basically now we show that this is possible because we can keep, so we take this guy, we purify it, we keep this phi here, and then we minimize it. So then we find psi and gamma such that the saturated equality here, right? Okay, and then the next thing is that you just show basically that you can relate this, the overlaps of these vectors, this, okay, you can read in the script, but the idea is really that the overlap is these 3 vectors. Now this is basically, so for example, I can then fix, phi is the state 0, right, in the computational basis. And psi is some state cosine theta, cosine alpha, 0 plus sine alpha, some other state, 1, for example, right? And then gamma is some state cosine beta, 0 plus sine beta, some state 1 prime. So they all kind of live in a 3-dimensional subspace. Okay? And all the overlaps, then you can see them as basically overlaps of states on a sphere. Yes. So we take this as a state 0 here, and then we have 2 states somewhere here and here. And then the angles between this quantum states are just the same as the angles between these vectors. on the sphere. And we know that the angle is a distance for vectors on the unit sphere. Okay, so then the triangle inequality is satisfied, right? So it's not crazy. So yes, so indeed we show that it's an angle, and now this. So okay, so now why is it nice? Because let's see what we get. So right, let's see. Let's get the angle between neighboring states. So rho of b and rho of b plus db. Yes. Yes. Basically, by inverting this relation, right, we see that f of rho and sigma, this is a cosine of, so sorry, what is it equal to? Well, since f is rho and sigma, this is equal to cosine of, rho of b and rho of b plus db, right? This is equal to cosine of the angle, rho of b, rho of b and rho of b plus. So, right, so we get that the cosine is, so let's just, cosine is 1 minus 1/2. Since this angle is small, right, around 1, we'll just get 1/2 dA, right? Where dA is precisely the angle between squared. This is the definition of fidelity. Right, so the cosine, so we have a cosine of some small angle here. If you expand it to the first order, right, you know that the cosine is just 1 minus 1/2 the small angle here. So the fidelity is the cosine of this angle. Okay? On the other hand, we also know that the fidelity is just given by 1 minus the Fisher information, dB squared, with a factor of 1/8, right? Is this correct? I can't remember if it's 1/8 or 8. It's so embarrassing, right? When it's divided by 8 here, right? This is correct. Okay. So yes, okay, it's dB, of course, is not here, but here, right? All right. So you see that the things that are equal. Then basically, if you expand the angle between these two things, then dA squared is equal to 1/8. So dA squared is equal to 1/8 things. So this is equal to so we get dA squared is equal to check 1/4 Fisher information times dB squared. Right. So in other words, this thing is we take the square root. So the angle for small. So for neighboring states on our curve, this is just equal to 1/2 square root of the Fisher information of the state times dB. Okay. Very nice. So now we see what we have. So another interpretation basically is that the Fisher information, if you have this angle now, which for pure states really corresponds to kind of a natural angle you get on this big sphere of states, then you see the angle. So you can see the Fisher information is actually the angular velocity, right? So how fast the angle increases when we change the parameter. Yeah. Clear? So now why is it nice? Because the angle is a distance. So this is alternatively we can define the Fisher information like this. We just show that this is all the same story. Now let's keep this in mind. So I just started here. So dA is equal to 1/2 square root of Fisher information of the state. The parameter. Now let me draw this curve. So now we have some big space. We have this curve, right? And we have here rho of 0, for example, right? And here we have rho of b. Okay. And for example, we care about actually the angle between these two states. So let's say what is the angle between rho 0 and rho at b? Yes. Well, what we can do now is then we just divide this curve in small steps. All right. And then by triangle inequality, we know that the sum of angles here along this path can only be larger than the angle between the final things, right? This is precisely what the triangle inequality tells you. So in other words, this angle is smaller or equal than the integral of 0 to b, right, of dA between rho of b and rho of b plus dB. Nice. So this is what we do here, just we integrate this angle, obviously, on the path. Okay. And this clearly now is just equal by this thing. This is equal to integral of 0 of b of 1/2 square root of the fish information of rho of b dB. Okay. Now, in many cases, for example, when they have pure state, or when they have unitary encoding, you see this fish information is really independent of the parameter b. It's always the same. Right? So, if, for example, if the fish information of rho of b is just a constant, right? So independent of b, or if you just kind of can use the max here, then you see that this thing is smaller or equal than, well, we just integrate it 1/2 times b times the fish information max square, right? So what does it allow us to tell? Now you see that basically, for example, if we go back to fidelity, then this thing tells us that, for example, the fidelity between the final states rho of 0 and rho of b is actually bigger or equal. So you take the cosine is kind of the Euclidean function, so it's bigger or equal than the cosine of b over t times the fish information, or the integral of the fish information. So if it's constant, it's just like this, right? And for example, it's nice if b is actually the time. B parameter is really the time, so the evolution along this path now is given by just the evolution in time. Then you see that this thing, this is relationally called speed limit. So they tell you how fast the states can get orthogonal, right? So you see that if the fish information of the state locally is small, right, then it really gives you a limit on this time b. So let's put time here now. So then we have actually rho 0 now is rho 0 and rho is rho of t. Then we can see that the state cannot get orthogonal faster than a time, which is what? So this should be pi over 2, right? So pi over 2 is equal to t over fish information. So then, in other words, time should be bigger or equal than 1 over the fish information. Yes. So this is a kind of, so it's a speed limit. So it tells you that if you want to, either in presence of field, or just for example, if you have some master equation, right, and you can bound the fish information period in time, so how fast it changes, then you can know that you need some time to get to orthogonal state, right? So it's really, I mean, we can play with this. It's really kind of a very powerful tool, the speed limits, right? And you see that we really just get it from the fact that this angle is the substitutability. So the angular velocity is given by the fish information, and that that the angle is the distance. So we can break it down in small intervals. All right. I mean, maybe we can have a nice example later on, but it's really very useful sometimes, this kind of relation. Yep. Nice, so that's it for today. Well, the proof for this angle thing is in the script. I forget to put the recording on for the second hour, so we'll just get the end. But there is a script. So. Do you have questions on this, or?